So I thought I showed people some of what it looks like for me at the other place. I am sitting in front of an electron microscope. This is a transmission electron microscope, and I'm using it to analyze currently a piece of manganese for a standard. But you can see our computers here. This is the scope. If you look here, what we're looking at up at the top here, this is the electron gun. Think of it as sort of a miniature particle accelerator. At the top there's a filament that generates electrons, and it shoots it straight down this column. It's directed by magnets down this column to this thing here. This little rod here holds the specimen. It's placed inside this column. Comes down, and I'll turn the light off real quick. Comes to this screen. This is where we do our basic analysis. What you're looking at right there, and we'll tip it up. That little structure, it's kind of hard to see, I understand. I'll put this little pointer thing. The pointer right there is pointing to the asbestos structure. That one happens to be for asbestos type called crucidilated. Those little round things you see are artifacts of the filter that we use. It's a polycarbonate filter. Okay, now, when we analyze asbestos, the first thing we do is we see it here. And then what we do is we have to determine its morphology is correct. In this case it is, and we have to determine its chemistry is correct, in which case it is. We'll just have to take that as an assumption right now because I'm not going to pull a spectrum. But the next thing we have to do is take a picture, and that's accomplished of its diffraction. That's this crystal makeup. And that is accomplished with this camera right here. And you can see the lead shielding there. This camera is linked to this computer here. And all this is a version of software that's used for scientific imaging. It also runs telescopes and other electron microscopes. And once it's done with that, I'll have a diffraction. I measure the crystal spacing so that we know the internal structure is correct. And then I will determine the chemistry. That is done by taking the beam, what we just saw there, that green bit, see it? I shoot it with the beam. The beam comes down from the column, impacts the structure right here, and then after it impacts the structure, so if you imagine right dead in the middle of the screen here is where that fiber is. It comes down, it hits, and then off the side right here is a detector. This detector is also part here. Now this detector detects the X-rays that come off of that structure that's right there, and he uses the liquid nitrogen cooled detector, sends a signal down to this monitor, and in this case I was pulling a manganese structure for my calibrations, but we get our spectrum there. Once we're done with that, we take a morphological picture, and we move on. What we're looking at here is this particular scope is a scanning transmissive electron microscope, or a STEM. And we can do things like, coordinate, location. This is what the scanning portion looks like. I don't know how well that's going to look. Let's see here. Let's focus it in a little bit. There is our asbestos structure. We're going to zoom it down. Now, this only goes to 100,000. No, it goes up higher. They've fixed it. This one has a fairly decent magnification. We're right now at 120,000 kx, or 120 kx. And now it's at 300,000 magnification. 400, 500. I'm not focusing it because I'm not wasting my time doing that. But here it is at 20,000. This is the magnification we do our analysis at. And the analysis here is done at 20,000 as well. So that's one of the machines we work at. There's my lab notebook, taking notes. So that's it for now. Maybe one of these days I'll do some more